Okay, we're live on YouTube.
Do you want to introduce the speaker? Cool. Good evening, everyone. How are you doing? Ready? Woo! I have another general meeting. Welcome to the June Los Angeles Astronomical Society general meeting. So stoked to see everyone here. It's been a while, hasn't it? All right, so first off, I want to see, are there any new people here, guests or visitors? Can you raise your hand?
We must have at least one new member.
Oh, Gio! You count.
Is there anybody who needs a raffle ticket?
Yes, does everyone have the raffle tickets?
I gave you one.
Okay, introduce yourself.
Oh my God! Oh.
Big round of applause for Gio.
Woo, hey guys, welcome. Good to see everybody. I happen to be in the area operating the Celostat up top, and thought I'd stop by and say hi. It's been a while since I've been to a meeting, but I do see all of you up when you go to Mount Wilson, so keep coming up, because every time you come up, Daryl brings food, and I love food. So please keep coming back so I can get more food. I need more food. Thank you guys.
Yay.
Great to see you here. All right. Anybody else? Are we good? Okay, let me get back down here. All right, so we have some events coming up. We have a star party this Saturday. Woo! It'll be exciting, going from 2:30 to about, what, 10 o'clock at night? Yeah? Oh, they chase us out around 9:30. All right, so 2:30 to 9:30. But it'll be exciting, really exciting. There should be some good things out there tonight, or that night. Let's see. Do we have any other events coming up? We have Garvey Night this Wednesday, which is exciting. We're also going to be upgrading the internet at Garvey in the coming month, which will be really exciting. So that'll be good Wi-Fi for once. Let's see. Oh, we have online? Yep. We have the people online too. All right, so we're going to have a raffle tonight for door prizes. So make sure you get your raffle tickets and make sure that you follow the link if you're online to enter your information for the raffle online as well, so that we can see who wins and send out the information from there. So I think that covers it for events coming up. I don't think we have any outreach in the immediate future. We do have a board meeting on July 3rd, and then I think that's about it, right? Yeah.
Well, the general meeting in the second Monday in July, whatever that is, I think I know what's going to happen.
Yeah, I think the general meeting's on the second Monday of July this time around. So that's it for upcoming events. So without further ado, I'm going to let Tim Thompson here introduce our speaker for tonight. Tim's our local astronomer, astrophysicist, amazing, and President Emeritus. So let's give him a big welcome.
Merci beaucoup. Our speaker is zooming in this evening. You almost got stuck with me again, but at the last possible moment yesterday, I accidentally bumped into Warren Skidmore, whose face is up there on the screen behind me somewhere. His official title, if I get it right, is Instrument Systems Scientist for the 30-meter project. 30-meter telescope. That's the really big. 30 meters is like big, right? You may think you have a big telescope, but no, 30 meters is like really big. But they've been laying off people. I think he's like the last scientist left hanging around, so maybe he's just the chief scientist, the real scientist, and everything else. He can talk about that. But the last time he talked to us about the 30-meter was a couple of years ago, and things have happened since then. We have new members, and so thank you, Warren, for joining us this evening and teach us all about the Go.
Thanks, Tim. Can everyone hear me okay? Can you give me a thumbs up or okay?
We can hear you in here.
Perfect.
Yep, we can hear you on Zoom.
Excellent, excellent. So I'm just going to share my well, I'll start my presentation and share my screen. Let's see. One that should work. Can you all see that? Is that okay?
We see it.
Perfect, perfect. So yeah, I'm my name is Warren Skidmore, and because now it's not the slides aren't advancing now. So let's see. Yeah, so technical issues. So I'm Warren Skidmore. Let's see if this works now. No, slides aren't advancing for some reason. I don't know why they're not advancing. Yeah, I'm Warren Skidmore. I'm the instrument system scientist for TMT, and I can't. 5 minutes ago, I checked this and it was all working well. So I'll jump out of this mode and just have my big PowerPoint thing like this and hide my email and everything. So hopefully this will work okay. But yesterday, my arm is still hurting a bit, Tim, from all the twisting. I went up to Mount Wilson and with my kids and my wife, and we were just walking around, and we bumped into Tim, and Tim gave us an impromptu tour of the observatory, and he mentioned about the need for a speaker this evening. So thanks to Tim, and to sort of repay Tim's kindness yesterday, I wanted to come and I'm happy to give this talk tonight. So I work for the 30-meter telescope, and I've spoken a couple of times over the years to the society. Once a couple of years ago, again on Zoom, and once several years, well before COVID. But just for a recap, for those that are new and those that need a refresher, we trying to build this 30-meter telescope, 30-meter diameter primary mirror, and to do a whole range of different sort of science. It's a general purpose telescope with supporting a bunch of different instruments, and we want to bring new instruments in periodically as well over time to keep new capabilities coming. But it's a very traditional sort of telescope, a big primary mirror to collect the light, bouncing up to a secondary mirror at the top, a convex secondary, down to a flat tertiary mirror, the third mirror, and the third mirror is you can articulate it to send the beam to different instrument locations. So we have this 3-mirror telescope system that can feed up to about 8 instruments, something like that, depending on how big the instruments are. But it's it's a big mirror. Here's a little guy on the side. You can see this underneath a basketball court. That's the sort of size of the mirror, and it's a big project. There's international partners around the world. The big players are Japan, Canada, the US, and India. They're all contributing stuff, and I'll tell you a bit about that in a while. And one of the reasons I keep coming back, keep cropping up, is we've had delays in the project. Our primary site is Mauna Kea in Hawaii, and I'm sure you all know. There's a whole bunch of observatories operating there, and it's a fantastic place for astronomy. And our alternate site is the Canary Islands, La Palma in the Canary Islands, another volcano in the middle of the ocean. So the qualities of that site are very similar to Hawaii. but it's a lower altitude, so that there are some differences. Both sites are in the northern hemisphere, and that's important for TMT. Just talking about Hawaii, though, we've got delays in Hawaii because building projects in Hawaii, it's a very contentious issue, and quite rightly so. And I put my hands up. I'm not an expert in all of this. I'm an astronomer. I can answer questions about how we'll study black holes and things like that. But I have to acknowledge that I'm an astronomer. And we want to build this telescope in Hawaii because it's a fantastic place to do astronomy. But we are coming into the place as people that live there, that have lived there for a long time. The indigenous people of Hawaii have had a really bad history. So there's a lot of issues, problematic societal issues in Hawaii that manifest themselves in a way that makes it difficult to build TMT there. And TMT is trying to do its best to be a positive contributor to the community in ways which the community is defining. We don't want to come in and think we know how to help because we may have good intentions, but that's not the right way to do it. The best way is to get the direction from local people. But anyway, it's a long and rocky road that we're following, and there's a lot of work. I had this picture. This guy on the right in the red shirt, he's the TMT project manager, and then Kyoki on the left here is a native Hawaiian who is very enthusiastic about what astronomy can bring to the islands. And Yuko here is our outreach manager in Hawaii, and then they're all working together and working with lots of people to try to find a path forward for getting TMT built in Hawaii. Getting back towards science and technology and everything, we want to build a general purpose observatory. So this figure, spectral resolution on the left, most astronomy science isn't done with images, it's done with spectroscopy, because then you can work out the temperature, the chemical constituents, the kinematics of objects that you're looking at. So spectral resolution and spatial resolution on the horizontal axis here. The bigger telescope you get, the smaller the angle, the finer the spatial resolution is that you can resolve on the sky. We need adaptive optics on 30-meter telescope because it's on the ground. The Earth's atmosphere causes disrupts the light as it comes into the atmosphere, and we have to fix that. But once that's fixed, you get to the physically limited spatial resolution of a 30-meter diameter telescope. At the moment, we have 10-meter class telescopes, lots of 8 meters, so that they can't see such fine detail on the sky as we will be able to see with the 30-meter class telescopes. But and all these coloured boxes which are on this plot represent different types of instruments. Each box represents a different instrument that we are either building or plan to build. The green ones are ones that we're building, and they aimed at different types of science mainly, and I'll tell you a little bit more about that in a bit. But the telescope can, and the observatory can support a range of different instruments and do all kinds of different science, from stuff in the solar system to the most distant galaxies that have ever existed. So, why do we want to build a big telescope? I've started talking about the science we want to do. A lot of the science we can't do with existing facilities. I've got some numbers here. The spatial resolution, like I was mentioning, the James Webb Space Telescope has a 6.5 meter mirror. There's no way that can see the same spatial detail that we'll be able to see with a 30 meter telescope. This huge sensitivity gain. It depends how you look at it and what sort of instrument, what sort of observing mode you're using. But if you're using adaptive optics, a big rule of a common rule of thumb is that the sensitivity goes as the diameter of the telescope to the power 4. So you increase the diameter, like an 8 meter telescope to a 30 meter telescope. That's a factor 200 times more sensitive. What takes you 200 minutes on an 8 meter telescope takes you 1 minute on a 30 meter telescope. And the sensitivity gain can be even more than that. For exoplanets, it's more like d to the power 6. But if you're in seeing limited mode, optical spectroscopy, that sort of thing, it's just really d squared. But there's still that's a 10 times more sensitive than an 8 meter or 12 times whatever that is. It's a big gain in sensitivity. So this gain in sensitivity and this spatial resolution allows us to study the full history of the evolution of the universe, looking at the very first stars that formed in the very first galaxies, of primordial hydrogen, helium, lithium, and after that, all the other elements started to get to be formed. Getting that full history is something that a 30 meter telescope can give us, and at the moment with existing facilities we can't really get the full story. With a ground-based telescope, the instruments can be very much higher spectral resolution spectrographs, much bigger images, wider fields of view, this kind of thing, much more sensitive, higher precision, higher performance instruments. You have those on the ground. Stuff that you launch into space has to be very rugged, and if it breaks, you can't fix it. Stuff on the ground, you can have much higher performance instruments, and that allows a lot of science. And I'll tell you a little bit towards the end about something where I was last week, in fact, thinking about the science we want to do with these things. And we're building the telescope, and we're building some instruments, first light instruments, that I'll tell you about, and we have plans for future instruments as well. So this was going to be a nice graphic if my presentation had worked properly, but let me just move these out of the way a bit. So we can do science in our Milky Way, looking at exoplanets, the supermassive black hole in the center of the galaxy. That's a big science case. And then moving out into the local group of galaxies, looking at the characteristics of dark matter, looking at dwarf galaxies, for example, and measuring the position of the stars in those dwarf galaxies, and coming back a few years later, and those stars will have moved. They're moving around in a dark matter halo. Trying to understand the characteristics of dark matter is something that we should be pretty good at doing with 30 meter class telescopes, because we have that very high sensitivity. We can see lots of stars, lots of faint stars, and with good astrometric precision, measuring the position of things very well, fundamentally because of the good spatial resolution that we have. And then I've talked about the distant universe, how supermassive black holes grow from whatever seeds them in the early universe to some of the huge ones that we we see today. One of the big results that's come out from James Webb Space Telescope is that we see big black holes much earlier in the history of the universe than we expected. So what's happening? We don't. We got to learn what's going on, and we need a 30-meter class telescope to be able to essentially zoom in on those early galaxies and dissect them spatially and spectrally to find out what's going on inside. And but James Webb's limited at the moment with its spatial and spectral resolution. So this is the center of our galaxy. What we can do at the moment with the Keck telescopes and the upgraded adaptive optics they're building for that. And then with TMT, I don't know how well you can see it. You can see lots and lots of faint stars in this image, and lots of those stars are whizzing around the central black hole very quickly. They're going much deeper into the gravitational potential well. So we'll be able to do tests on general relativity and modified theories of gravity and things like that we just can't do with today's instruments. Even the down at the VLT interferometer down in Chile, they can measure extremely precise positions of things, astrometry, better than we'll do with TMT, but they don't have the faint object sensitivity. They can see a few bright stars in the center of the galaxy, but they can't see lots of stars, which is what you really need to be able to do. So this is a similar plot. This is what James Webb sees when it looks at the center of the galaxy. This is what Keck sees at the moment, and this is again what TMT is going to see. So you can separate all of those stars. Push back against the confusion limit. So as something I'm saying here, all new and improved science utilizes essentially one of two things: the ability to resolve individual stars, measure their positions, and or the sensitivity to study faint targets. Building a bigger telescope will increase the sensitivity with the adaptive optics. That really enhances it a lot. Let's see. Let's move on. So, this is a bit of a jumbled image, but we're building a telescope. We're building some instruments, and the first three columns here are the first light instruments. If I turn your eye to the bottom right corner here, so that's an image of the telescope that I showed right at the start. And I don't know how well you can see at the sides of the telescope, there are these sort of tennis court sized platforms. And those are where the instruments go. And there's a blue box here. That's the adaptive optics system. That I'll mention that in a moment. And you can see another instrument over on the other side here. This one over on the far side, the right side of the image here, is actually this one over here on the left side of this plot, the wide field optical spectrograph. The project scientist for this is at Caltech, and it's as big as a house, but it works in the optical from 310 nanometers, which is that's actually UV really, actually into the infrared UBVRI wavelengths, and it's a multi-object spectrometer. So if you look at a patch of sky and you pick a bunch of targets, perhaps up to about 100 targets, you can do we create a little slit at each target. We have this thing called a configurable slit unit, which is being made with bars that go in and out, and in between two bars there's a little slit, the slit for the spectrometer, and then we've got 100 pairs of these bars, and so we can have like 100 targets and do spectroscopy of up to 100 targets. That could be galaxies or stars or whatever your science needs. So that's one instrument. Then the next two instruments are both fed by the adaptive optics system. I'll tell you about that in a second. So these are near infrared instruments, going from about 800 nanometers, 840 nanometers to 2.4 microns. That's the wavelength range. And this first instrument is it's a two-channel instrument. The first part is an imager, and in the bottom here, this sort of orangey picture, that's an image, a simulated image of what we expect to get from this instrument. And the field of view of the imager is 34 arc seconds on a side, and so that's about the same as a if you put a period, a full stop on your finger and hold your finger at arm's length. That's the that period represents the field of view of this instrument. But when you connect it with adaptive optics and you look out into the distant universe, you see a lot of targets. This simulation is actually the center of our galaxy, and there's 4 detectors in the imager, and each one of them, they think they should see about 100,000 stars in each one. So it seems a small field of view, but coupled with a big telescope, there's a lot going on there. And it's diffraction limited as well. The pixel scale is diffraction limited, so you'll get the finest spatial scale as well. On the optical axis of this instrument, there's another part of the instrument is an integral field spectrograph. So this little image down here shows a data cube. Instead of just having an image, every pixel is stretched out into a spectrum. So you end up with a data cube. X, Y, and wavelength is what comes out of this. And this field of view is very, very small. It on the finest spatial scale, it's about 1 arc second field of view, sampled at the diffraction limit, which is 7 milliarc, or Nyquist sampled actually. So the spatial scale is about 4 milliarc seconds. And then this is an instrument which is extremely useful for looking at those distant galaxies. Little distant galaxies, some decent size, decent fraction of an arc second across, and we can see we can spatially resolve the galaxy into lots of spatial elements, and look at the star formation processes as a function of position across the galaxy. Look at the internal kinematics. If there's one area where all the stars are moving fast, around a black hole or something, we'll be able to look for those kinds of features in the distant universe with this, and do a lot of look at asteroids, look at the composition and shape of asteroids, things like that. It's a very versatile instrument. This other instrument, this multi-object diffraction limited high dispersion spectrograph MODIS, is fed by the adaptive optics system. This IRIS instrument hangs underneath. This MODIS one sits on top. Well, part of it sits on top, and the light from the science target goes into optic fibers just down onto the platform into these suitcase-sized spectrographs. Very small spectrographs, but very high resolution, very stable. And they can be made small because we're using optic fibers which are fed at the diffraction limit, very small images. So that it's a very good design, really stable, high precision spectrographs. And they've built a couple like this or at least one that they've used down at Palomar already, and they've got something over at Keck in Hawaii like this as well. And they're building something which is actually the same design as this that they're going to install on Keck in the next few years. So this instrument though is really for exoplanet work. So with the adaptive optics system, you get a beautifully corrected image. There's in the top end of the instrument, the front end of the instrument, there's a coronagraph. so you can block out the light from the exoplanet host star, and put the optic fiber right on top of the exoplanet, and exclude most of the contaminating light, and just get the light straight from the exoplanet, characterize that. And this is a high spectral resolution instrument, so it'd be very good for looking at whatever molecules and things are in the atmospheres of exoplanets. But it's also used for, without the chronograph, just for measuring the radial velocity of the host star. So the more, one of the traditional ways of finding exoplanets, looking at the recoil of the host star as the planet orbits around. And then the third thing it can do is when a planet passes in front of its host star, and some of the light from the star passes through the atmosphere of the planet, we can do transit spectroscopy. So you look at the host star with and without the planet in front of it, look at the difference, and you can tell quite a lot about what's the constituents of in the planetary atmosphere. So the searching for biosignatures. This is the thing we shall be doing it. This instrument. Looking for signs of life. And so these last two instruments are fed by the adaptive optics system, which is in this fourth column, and this is being built mainly up in Canada. Things like the deformable mirrors are being built over in France at the moment. I don't know if they've been finished. I'm not sure what the status is, but it's in fabrication basically. The light comes in about here. There's one deformable mirror in here, one deformable mirror over here, and it can feed up to 3 instruments on the output here. And when we're building that from day one. And what I want to mention is that this uses laser guide stars. So there isn't always, you always need a star or multiple stars to measure the turbulence in the atmosphere, and then to correct for it. You need those stars to be near your science target. But there isn't always stars conveniently close to science targets. So we're planning to use, and we're building a laser guide star system, which uses an asterism of 7 stars on the sky. And you can point the telescope almost anywhere and do science with it. And I'll tell you how that is a problem or a concern that we have to deal with at the moment in a bit. Just a bit of a technical sort of update. There's lots of work being done on stuff to do with the mirror. These the supporting all this glass that we need in the primary mirror. 30 meters worth of glass. 492 of these segments. These segments are 1.44 meters from point to point, or corner to corner. 492 of them, and as of the other day, we've polished 117. We've got about 400 blanks, round blanks. We've polished 117 of them. We've built a lot of this support structure that goes at the back. We've got several hundred sets of that, but what we haven't produced yet, we've made lots of prototypes. We haven't got any production units yet where we've chopped the corners of the round polished blanks and mounted them to the support structure. That's the next step. But we've got polishing lines now in Japan, in India, and up in the Bay Area north of here. And so actually the up in the Bay Area, that's where they're doing the majority of the polishing. And then all this support structure stuff. This is all being made over in India, but it was all designed over at JPL. Let's see, up in the Bay. These are pictures from up in the Bay Area. These roundels, these polished roundels. get inspected and made sure they're perfect. And there's just some pictures of what's going on up further north from here. So we have a lab over in Monrovia. Let me see if I think I've got more pictures. Lots of pictures. There's lots of hardware development that's going on over in Monrovia. And I want to invite, if you guys are interested in coming for a visit one day, come over to Monrovia and I'll show you around the lab one evening or at the weekend or something. We'll have to close the loop about that. There's lots of work going on, and we've got this pretty impressive thing over there, which represents 7 segments, and it's got all the control system behind it, and it's just been used for testing and fitting and making and testing performance as well. And it represents one little part of the primary mirror, but it's a super useful piece of gear, and it's quite impressive to see it. I mentioned that we're going to be using laser guide stars for our adaptive optics. The laser is a sodium laser. We've got a whole bunch of them, a whole bunch of sodium lasers. The laser light gets sent up to a launch telescope at the top end of the telescope behind the secondary mirror, and this asterism of guide stars is projected up, and then there's this layer of sodium about 90 kilometers up in the air, that in the atmosphere, that glows. The sodium comes from meteors. And anyway, so the sodium glows and makes fake stars that we can then use to measure the turbulence. The trouble is, most of the really cool science we want to do with the future big telescopes, not just TMT, that almost always requires the use of laser guide stars. A huge amount of the science relies on this. But if for US facilities, at the moment, there's a policy. If you're using a laser guide star for astronomy, you have to clear everything with the defense, the laser clearinghouse. And there's this old policy, the US laser deconfliction policy. They didn't want to cause any sort of international incident where they launch a laser and damage a satellite from another country and cause an international incident. So a long time ago, they set up this laser deconfliction policy, and US facilities are bound by this. For the military, it's much more relevant because they do use lasers for illuminating enemy spy satellites and things. So it's important for them to know what they're doing. But it's less important for astronomers, because most countries don't follow this rule. And there's never been any incident where some astronomers have damaged a satellite with a laser. It just has never happened. But if you're a US facility or on US soil, you have to turn your laser off whenever the laser clearinghouse tells you. And so at the moment, there's a few thousand satellites in low Earth orbit. And like the Gemini Observatory, for example, when they're using their laser, they have perhaps up to 10 closures. They have to turn the laser off, sometimes for a couple of seconds, sometimes for a couple of minutes, every night. Every time they're using their laser, about 10 closures per night. But when you turn it off for a couple of seconds, you don't just lose a couple of seconds of observing time. You have to reproject the laser, acquire all the laser guide star images, and close the adaptive optics loop. You lose time. You lose a couple of minutes, a few minutes every time you turn the laser off. So you might lose half an hour a night, say, with a few thousand low Earth orbit satellites. But there's a lot of satellites getting launched at the moment. And so and I'm sure that a lot of you guys who do astrophotography, you see this. It's a right pain. All these low Earth satellites which are getting launched, and potentially there could be well over 100,000 satellites which are getting planned to be launched. Luckily, they've started to do things like paint them black and make sure that the specular reflections are minimized and things like that. But they're still up there, and that doesn't help this rule with the laser clearinghouse. So we're involved in efforts at the moment to do studies where we're looking at the risk of illuminating satellites with a ground-based astronomical laser, and we can wave our hands and say, "Oh, the risk's minimal," but we're doing a formal study to sort of to back that up, and then that should inform the policymakers, the lawmakers about this, and hopefully we can get a change in the rules, which will mean that we can actually do lots of science with the 30-meter class telescopes. Because if we don't change the rules, it's going to be a real big impact for what we want to do. I haven't got many other slides. I've got a couple more things like news items to tell you. Science changes. A couple of years ago, 2.5 years ago, the James Webb Space Telescope was launched. This was a big deal. The number of results which are coming out from the James Webb Space Telescope is incredible. One today, they're finding 10 times as many supernovae in the high redshift universe than they expected. That's what a new result from James Webb Space Telescope. We have to get our thinking caps on and figure out what's going on. And there's new results coming out all the time. And how does the science change? Do the changes in the science impact our plans for the 30-meter telescope? We have this big book, the 30-meter telescope detailed science case, and there was one in 2009. This is the 2015 edition. We updated it again in 2022, and we're doing another update right now. And this photograph on the left is a meeting I was at last week over in Japan. I just got back on Saturday. We were there talking about the science we want to do with ELTs, given all this stuff that's coming out from JWST. And what's amazing is JWST is an incredibly powerful machine, incredibly powerful telescope and instruments, and it finds things which we don't expect, and its limitations mean we can't really move forward with studying that. We find these questions, we uncover new questions, and the next thing we need these 30-meter class telescopes to make the next step forward. It's quite a common story that seems to be coming up every time we look at the science. The science does change, but the fundamental capabilities that the observatory has to provide, you still want diffraction limited imaging and spectroscopy, optical spectroscopy. And for the JWST stuff, it's normally this stuff which is adaptive optics fed, near infrared observations. They're the big ones always for JWST science. But that's what we're planning. We're planning to provide the capabilities for following up on this sort of stuff. And if every time we look at the science, we look at what we need in terms of observing capabilities, and we find we're in a good place. We're planning to provide this stuff. This is my last proper slide. There's this thing called the US Extremely Large Telescope Program. So I'm in, my office is in Pasadena. In Pasadena, there's the office for 30-meter telescope and the Giant Magellan telescope. Now, over in Tucson, there's this place called Noir Lab, the national. I don't know what the NOIR stands for anymore, but it's where they coordinate all of the US telescope time. And I'm on a telescope allocation committee. We get all these proposals to use telescopes, and we have to rank the science and see how exciting and fundamentally important the science is, and then it gets ranked, and they know how much time they have, and they cut off, and the ones that get given time, get awarded time, that their observations get taken. But Noir Lab manages all of that, the proposal process, the assessment of all the proposals, that sort of thing. So these three groups, TMT, GMT, and Noir Lab, are working together to provide access to use these telescopes for all US research astronomers. And you propose to use one or other or both telescopes, and there's a full data archive as well. And so these three groups, that's the US Extremely Large Telescope Program. Giant Magellan Telescope's in the south. TMT is in one of the northern hemisphere sites. So we've got the whole Earth or the whole sky covered with this, which is unique. The European Extremely Large Telescope's in the south, so there's parts of the sky that it won't have access to. But there's a few things. Well, one point, all of these groups, TMT, GMT, and Noir Lab, we've all now received some level of funding from the NSF. So we've all got our business practices set up so that we can receive federal money and that kind of thing. But the amount of money that we need to build these telescopes is huge. It's bigger than any previous project that the NSF has funded. So that we're breaking new ground. So that makes the NSF, the National Science Foundation, is very cautiously moving forward, reviewing the projects. And one thing, GMT and TMT, the two telescopes, we passed our preliminary design reviews. That's, there's a conceptual design, a preliminary, then a final design review. We both passed our National Science Foundation preliminary design reviews 18 months ago. So that's good. Let me see. So this is my last slide actually that I was gonna talk about, just to go through. So we are planning to build this big telescope. There's technical progress happening. Instrument design is going on, and building mirrors and things like that. There's this US Extremely Large Telescope Program, which is very exciting in terms of trying to coordinate the two big telescopes that the US is involved with. And then I mentioned about the efforts of engaging the local community in Hawaii. And I wish I could say more about that, but it's not my area of expertise, I'm afraid. But there's some heroic efforts going on over there, and I want to acknowledge that, recognize that. And then because I know some of you guys will be getting impacted by these satellite mega constellations. It's not just astrophotography and amateur astronomers. The professional astronomers are going to get affected as well, but for sometimes different reasons. And for us, it's this laser laser guide star issue, which is the big problem for us. And then I wanted to just reiterate, you know, you can leave your contact details with Tim, or I'll just put my this is my email address, and so take a screenshot of that. If you're interested in coming to the lab, I'm happy to organise something. The lab's in Monrovia, so might be fairly close for some of you, and sometime in the weekend or an evening, I'm happy to have a set of you over. And one thing that's cool is if you've got any non-astronomer kids, but they're interested in engineering and that kind of thing, bring them, because it's an engineer. There's a lot of engineering that's going on there, and we can talk about project management and systems engineering and that sort of thing. So that's an open invitation. So I better stop there, Tim. Otherwise, I'll be talking all night.
Okay. Thank you. We should have a contest between us to see which one can talk all night the most. So is there a question for Warren here in the auditorium? Oh, somebody must have. Nobody has a question. Okay. How about online?
See Terry.
Yeah, can you hear me okay?
Yes, perfectly, Terry.
We hear you.
What's the total number of segments in the TMT?
So in the main mirror, I'll share my screen again.
Okay.
In the main mirror, there's 492. And then we need, you see this six-way symmetry?
Yeah.
We need a full set of spares. Each segment section here has 82 different types. The segment shapes here in every segment. Well, there's 82 different segment types. So it's 492 plus 82, whatever that adds up to, Terry, in total. Okay. And the reason we need the spares is we take a dirty one out and put a clean one back in, and cycle through them that way. So that's why we need nearly 600 segments in total.
How are they figured? To what curve? Or are they sections or segments of a paraboloid or what?
It's a hyperbola.
Hyperbola. Okay, so it's a Ritchie-Chrétien system.
It is a Ritchie-Chrétien system, yes. And this is a hyperbola, but it, it maps to some. Each segment has a slightly different shape from its neighbors inbound or out, inboard or outboard of it.
And how do you test them? You've got interferometry, or is there something else you're doing?
See. I did have a picture may not have it here. No, I don't have. Oh, wait a minute. Yeah, look, I don't know how well you can see this. It's still Terry, right? This is some sort of interferometer, and I don't know the details. I'm not an optical engineer. There might be people in the audience that can recognize what this equipment is, but I've seen, I guess, interferograms of the surface, and you can see the the swirling from the polishing tool and that sort of thing. You can see the peaks and valleys, but as long as it's flat enough, then as long as it gets within spec, that's okay.
Yeah. Okay.
As I recall, the Keck segments were stressed, and then they could just grind and polish a sphere into them, and when they take the stress off, it relaxes into the shape. Is that the way the segments for the TMT are being shaped as well?
Exactly, stressed mirror polishing. So bend the glass, polish it as a sphere, and then let the glass relax into the back into the hyperbolic shape that we want, or the piece of the hyperbola that we want.
Are there any other questions from the Zoomies?
Yeah, you said that SpaceX voluntarily pulled out of the laser clearinghouse. What does that mean? What are the
Oh
implications?
yeah, they don't care if the Starlink satellites get hit by a laser. There's no optical sensors on them. You know, the power that the 300 miles high or whatever, 250 miles up from the laser, you know, it's actually it's a diverging beam, so it it's pretty spread out, so it's not going to do them any harm. And so they voluntarily have pulled out. They've said, do not include us in the laser clearinghouse thing.
Good.
But they're not, the laser clearinghouse folks are not going to, that's not going to be the default. The default is you include everything. There's even like space junk and pieces of debris and stuff which is in there because no one has said, a dropped wrench is it's okay to illuminate it. No one's ever told them that, so they have to include every bit of junk that's up there. Which it is a problem. It'll be a super big problem if these tens of thousands of satellite mega constellations get launched.
Hi, Warren. This is Alicia out here at Griffith Observatory. First off, thank you for the invite. We're definitely going to take you up on it. So look forward to invite from the board on that so we can coordinate with the members. Second off, what's the timeline for finishing this telescope?
Well, if we could start building tomorrow, it's still about 10 years to build it and do the sort of first light commission, get it ready for early science. But we're not going to be able to build it tomorrow or start building tomorrow. So what the next phase is, I could only guess really. The site situation basically is where the uncertainty is. We have an alternate site. We're doing our very best to push forward with the primary site, but what the time scale is for an outcome for that process is I couldn't guess. But if we could start tomorrow, it's still 10 years, so we have to keep physically fit and keep taking our vitamins and eat healthily, and eventually
keep our fingers crossed.
Yeah.
All right, thank you.
Okay.
As I reminded Warren yesterday, there are 5 telescopes at Mount Wilson Observatory, each one of which was the largest in the world when it was built, and they were all built over a span of 13 years. It's going to take them about 10 to build one if they actually start building it anytime soon. Are there any other questions in here?
Now, what are some of the implications of large satellite constellations on astronomy?
If I limit it to these big telescopes, in general, the fields of view of the instruments are very small. So the big impact is this laser clearinghouse rule and the use of laser guide stars. The chances of a satellite passing through the field of view is very low. It's not insignificant at dawn or just after just before dawn and just after dusk. For the polar orbiting ones, the sun synchronous ones, and like we've got that WFOS instrument I talked about, wide field optical spectrograph. There's an imaging mode on it. You can pull all the slits out the way and use it as an imager, and the field of view is big enough that we expect about 1% of the images to be affected if we're observing at the worst time of night, an hour or so after dusk and an hour or so before dawn. But during the middle of the night, it'll be very, very small. Moving to different types of telescopes, the Rubin Observatory used to be the Large Synoptic Survey Telescope. The Rubin Observatory is going to come online fairly soon, and that's it's a really big camera, wide field of view, and for them it's a real nightmare. The field of view is many moons, right? I can't remember exactly how big the field of view is, but the number of streaks going through will be terrible. And the Starlink satellites, for example, they paint them black now. They're painting them black, but they're still like 7th magnitude. So if you've got an 8-meter mirror, 7th magnitude is super bright, and you got a dozen of them passing through your field, leaving streaks. It is a problem, and there's a lot of effort being made to try to mitigate the impact. Anything which is wide field is a problem. But for the big telescopes, normally the fields of view are small, so we're much more immune to the effects.
Is this laser deconflicting office like a Defense Department thing that can be controlled by the executive branch, or does somebody have to pass a law saying you can go ahead and light up a wrench?
I'm not sure of how all the rules, and the laser clearinghouse is defense. It's Air Force or Space Force now, I guess. And they're, for them it's important. They need to know where their own satellites are, because if you've got a spy satellite that can read your license plate, you don't want to be shooting a laser at it. So they need to know where their lasers are, where their satellites are, and that sort of thing. But for regular astronomy, it's much more, things are not as critical. But I don't know what the official chain of command is, or where all the responsibility officially lies, and who pulls the strings, I'm afraid, Tim. I should know it because I'm supposed to present about it at the International Astronomical Union meeting in August. So I've got to learn all of this stuff.
Elizabeth had asked about how do you prioritize the proposals, and since you're on a committee that does that, maybe you can give us a little inside skinny on how to give a really good proposal. Well,
proposals, when we rank them, at least for the US, it's is it double blind? You don't know the name of the proposer or the institution or anything like that, and they have to write the proposals in a way which doesn't give away their identity and things. So that's one thing. The science has to be exciting. So the highest priority ones are the ones that have the best science. And then I work on the scientific ranking side. Once we've ranked all of them, then there's other people that look at partner shares. In the US, often there's different groups or different universities have time on telescopes, and say there might be, I'm just making up numbers. Say Caltech has 25% of time on the Keck telescopes, and University of California has 35%, and the remainder is through Noir Lab or something. How they're all not sequenced, how it's all allocated depends on partner shares. For TMT, we've got Canada, Japan, India, Caltech and University of California, and we want Noir Lab as well. So each of those partners will have to get their fair share of time. And like if all the Indian time has been granted, that'll be lower priority. So you got to make sure the Canadians get their time and the Japanese get their time and so on. So that then it becomes policies and rules to make sure that everyone gets their time. Then there's things like overrides, like if a gamma ray burst goes off or there's a gravitational wave event, you can interrupt, and then there's like some additional overhead, that's charged at 1.5 time or something like that. With these policies are TBD, but it'll be some sort of overhead, and whoever you interrupt will they'll get that time back and that sort of thing. Well, one thing I can say about the way time not so much is allocated, but it's implemented. What we're planning to have is an adaptive queue scheduling, that run in adaptive queue. So depending on what the seeing is, what the conditions are like, we pick the most appropriate science program given the conditions and all the partner share stuff and things like that I talked about. But the idea is that we can optimize the science that's being done to the conditions. And if in traditional observing, you might show up at a telescope and the seeing is brilliant, and you just want to do optical spectroscopy, which doesn't need good seeing. So that good seeing, which could have been good for exoplanet research or something, is not utilized. And then the exoplanet folks show up and it's snowing, and they don't get any observations at all. So adaptive queue takes into account the conditions, what fraction of time partners have remaining and have been awarded, that kind of thing. It takes all that, cooks it up somehow, and tells you what observing program you should implement next, and then the operator will implement that program.
When JWST went up, it had cosmology as a big deal, but they also looked at solar system targets. Is like Jupiter too bright for a 30-meter telescope?
No, you just zoom in a lot, as it were. There's one of the science cases looking at the vortices in the atmosphere of Jupiter, and using the Galilean moons as and other moons of Jupiter as the adaptive optics guide stars, which is a little bit problematic because they're actually resolved and they're not points of light, and they're also all moving around and that kind of thing. So no, it's not too bright, and in fact, it's one of the science cases is the vortices on Jupiter, and that to carry out that science case creates we need a lot of capabilities, and the adaptive optics system, it's really hard to it makes it a challenge to make that work, but it's all been designed to do it now, and we should be able to do it.
Terry, you had a question?
I've got two. The first is what are you coating these mirrors with, and how many times do you have to coat it to get the proper reflectivity? And the other one is, do you have an algorithm for what areas of the sky are covered by clouds and stuff like that, so that you might be able to fit somebody in who wants to look at something in the south while the north is all cloudy. I'm just wondering about that.
Well, so to answer the first question about the coatings, we're planning to, the baseline plan is to use the same coating that is used at the Gemini Observatory. It's a silver coating with a protective layer over the top, and those coatings work very well in the infrared, the far or mid infrared and near infrared, and they work pretty well in the optical until you get to the blue end, and then the reflectivity drops off.
Yeah.
But we or TMT wants to. We have requirements to perform well in the blue. The scientific reasons to do that. Yeah. Yeah. There's good scientific reasons to have blue sensitivity, UV sensitivity.
Yeah.
So we've got an active program to look at enhancements to the silver, the plain silver coating, to enhance its reflectivity in the blue, and we've got some amazing results actually. The reflectivity is really good to shorter wavelengths and even pass through the atmosphere. And at the moment, we're in a phase where we're testing the durability of those coatings. So we've got samples at various observatories. I think they might all just be in Hawaii actually. Just a big box of samples open to the environment to see how that lasts, because it has to last. The idea is we coat it once and put it in the telescope, and every 2 years we strip the coating and recoat. And because we've got 492 segments, it means we take a few segments out every couple of weeks and put clean ones back in, and it's a continuous process of taking out dirty segments and putting clean ones back in.
Mm.
And then the other question was about like for that USELTP program, if it's cloudy in Hawaii, could you do observations in Chile? Was that really what you were asking about, Terry?
Well, no, I was asking about the local sky wherever it is you put the 30-meter telescope.
Okay.
If it's partially cloudy down there, you could look up here. If it's partially cloudy over here, you could.
Yeah. Well, there's. You've asked a good question for me. I'm the work package manager for the site conditions monitoring system, and this measures a bunch of parameters which feed into that adaptive queue scheduling. And one of them is a cloud map, a transparency map. So, like if there's thin cirrus over there, but there's no cloud over here, you observe over there. If it's cloudy over there and there's a big hole over here, you'll observe through the big hole if you can. But if the humidity gets too high, this would be one of the systems which should alert you to that, and you close the dome and
Yeah.
if the wind is too high, that sort of thing. So I think the answer is basically to your question, yes, we will be able to utilize the best of the conditions that we have available to us. And if it's cloudy over here or clear over here, then we'll know that because we're going to measure it with the site conditions monitoring system.
Thank you.
Super.
One question in the chat, though, from Jeremiah. What are the two biggest questions TNT will answer, in your opinion?
There's two, the two biggest questions. One is it's more of an area than a single question, but it's the early evolution of galaxies. After the Big Bang, there was the universe cooled, there was the Dark Ages, and then eventually, after about 250 to 400 million years, the first galaxies were forming, and in those galaxies, what sort of black holes were around then? What was the star formation like at that time? How did those early galaxies start to reionize the universe? So there's a bunch of questions related to the very early, the earliest galaxies that existed, which are very interesting, and TMT is a good telescope for answering those sort of things. And then the other big one, in my opinion, is to do with exoplanet demographics, and looking at the different types of exoplanets which are out there, especially the cooler ones, and looking at the chemistry, but also the exoplanet formation process, the protoplanetary disks, and tying together the resulting exoplanets and what those compositions are back to the disks from which they formed. And I'm not going to go out as far as like finding signs of life, but just trying to understand the chemistry and the characteristics of exoplanets, especially the smaller ones, smaller, cooler, more mature ones.
Are there any other questions in the chat?
Hi, Warren. Can you hear me?
Yes.
Where does the money seem to be coming from for the next round of, telescopic mega projects? And how do you see the climate for financing being over the next, 10 to 20 years in terms of it being a bull market or a bear market for those kinds of projects?
I can tell you, historically, the biggest astronomy projects were in the last couple of decades or so have been mainly government funded, not just US government. The US government has been a big partner in things like ALMA and the Rubin Observatory and stuff like that. Then like ESO is a big organization, intergovernmental or external, it's sort of outside of governments, but it's an international organization where governments have committed to funding. So they have a lot of money, and they're building the ELT. In the US, we've got to break the previous pattern, or we need more money for these telescopes than has ever been given to any project before. So it's a bit hard to extrapolate, really. I know in the past it's largely been from governments. TMT has had a significant fraction from the Moore Foundation. That's been a big contributor. And then you've got things like the cosmic microwave background, the CMBS4, that observatory, and that's I think that's like a billion, almost $1 billion kind of project, and that's a lot of philanthropic funding, coupled with some government funding. The philanthropic stuff always seems to, the foundations put the early money in and get through some of the riskier early development. And then once you have a clearer path forward, then governments are more interested in investing money then. Well, I say investing, I don't know what the return is from an astronomy project, but yeah, they want the projects to succeed in their aims, at least. And so I suppose it's always going to be some combination of foundations and rich people and institutions and then governments as well. So it's a pretty good answer, I'm afraid.
So what I'm getting is kind of a traditional model rather than a more modern privatized model, and maybe beneficial in that you can be a little more pure science and not as commercial results driven.
Yeah, I think you summarized that. Yeah, I'm not
So-
sure I meant that, but I think what I said was in line with that, and I think
So you have to go begging a bit more than some of the ones that have more immediate applications, mega projects.
that's true. That's true. Yeah,
Thank you.
super.
So your current funding for the early development work, is that primarily foundation or private money, and then you hope to get NSF funding for the actual construction? Is that what I'm reading into this?
Well, we've had funding from or through the Moore Foundation, but that's been pretty matched, I think, with money from Caltech and University of California. And you know, and I don't know the exact, you know, I don't know the dollar values off the top of my head. But then as the project has matured, we've had you know, Canada's joined, Japan has joined, and India has joined, and each of those countries has provided in-kind stuff, which is money that's spent internally to that country, but it still has a value and essentially buys observing time. And they've also provided cash to the project for, you know, just, you know, running the project and the stuff which is not easily allocatable to an individual partner. Japan is building the telescope structure, the providing a whole bunch of the optics, the glass for the mirrors, bits of the instrumentation. India's done a lot of the software development and he's working on instruments and polishing. Canada's building the adaptive optics system and is what else is Canada doing? There's these in-kind contributions from the partners. Caltech and UC are involved in instrument development, although some of that I think is essentially it's contracted by TMT from the cash that comes into the project.
I think it's time for us to say thank you, Warren, and we will get on with our door prizes.
Okay, I'll answer Jeremiah's thing in the chat. Okay.
Yeah, you can submit your name for a door prize. You know, put your name on the list.
No, my prize is your company, Tim.
Oh boy, thank you. So I'll turn it over to Alicia, and she'll tell you about the door prizes. If you're online, sign in.
Well, before that, I have to go over some committee reports real quick. So where you started hearing back from planning and zoning for Lockwood and the vision workshops that have been held, they're starting to compile that information together for the next meeting. Yeah. And we also have scouting outreach coming up in July 17th and August 14th. We also have the potluck swap meet on July 20th. And we have family night on July 27th and August 24th. So look for that in the calendars as well.
Don't forget you already said it, but remind them again, the star party is this Saturday.
Right, and the star party is this Saturday, so don't forget about that. And the next one is on the 13th of July. Cool. So, door prizes. We have a. Are you guys already online? Have you submitted your Spencer?
Let's see. I think I've got about 8 people who submitted their names, and there are about 20 on the Zoom call.
Where's Spencer?
So if you are
okay. While we're
those
figuring out
of
what's
you
going
who
on
haven't
online, let's
submitted
talk about
your
what we have in
name,
person.
go ahead.
All right, we have a Celestron binoculars. We have the Observer Sky Atlas. We have a red flashlight. We have 2 green lasers. And I think that's it for in person.
Ready to go?
Yeah, so let's do the in person first.
Are you still connected online? Yeah. You can't hear me?
All right.
can-
First number is 833-4876. 4876. Oh, you're kidding. Is your mom? Again? You got it. What'd she get? You won a laser, just what you need. Remember we talked about this at the beginning. Oh my God. Okay. This is not rigged, I swear. Yeah, right. Every week we get like this. Sorry about. Okay, next one. Here we go. 833-4864. Well, I hear yelling and screaming up there. Oh, she won. All right. Yay. Coming down. Let me check the number. We're good. Okay. And what did she win?
She won a laser.
You won a laser. Oh, that's an oh wow, folks. Okay. Don't forget, wows are great, but oh wows are even better.
Well, what do you mean he's getting the laser? That's how this ended up, I guess.
You want to make sure you charge it. Okay, you're all set. Okay. Okay.
Can you hear us?
So we got
We'll do online.
next one. All right, online. Go ahead.
Oh, you want to do online?
Yeah, go ahead if you want. Yeah, it's up to you.
Spencer, do online.
Spencer, go ahead.
All right, here we go. Elizabeth Wong is the first one online.
Spencer.
What? Did I win something?
Yes. Uh-huh. Yeah. Elizabeth.
Yes.
We don't hear you, Spencer.
They can't.
What did I
hear me.
win?
Continue with the in-person until we
There you
That's
go.
okay,
Okay.
yeah.
Oh wait. Yeah. So he's going back to find out if he's okay.
I'm on. They can hear me on Zoom. They can't hear me in the auditorium.
Oh, you know what? Let me put it.
Oh,
back.
hang on just a second. Okay.
Oh.
Now, okay. Can you hear me now?
Yeah. Go ahead.
All right. So Elizabeth won. Go ahead.
What did Elizabeth win?
She won an LAS online store item.
LAAS online store item. She won. Yeah. All
Ooh,
right.
thank you so much.
You're welcome. And next, go ahead, Spencer. Spencer, go ahead. Is who?
Okay. The next one is Jose.
Okay.
Okay. He won a map of the moon.
Wins a map of the moon. Let's hear the roaring crowd going, yay!
Okay. Next one.
Next one, go ahead.
Okay. Andy and Veronica Jones.
They won an eclipse book.
You won an eclipse book. Congratulations.
Yay!
Yay. All right.
Okay, one more. Hold on.
One more for you. Go ahead, Spencer. Last one.
Right.
Did you want the mic? You want to do this?
You can do this part. I'll do the next part.
Okay.
Jeremiah Pitts.
Hot and cold Keurig.
A hot and cold Keurig item. How about that? Very cool. Actually, very hot and very cold.
Thank you. Appreciate it.
We do.
Okay.
All right. Yeah, we have 2 more for inside now. Let's do this. Okay. 833-4861. Yeah.
Oh, got a winner. Okay.
Yeah.
What does he win?
He won the Observer Sky Atlas book. Here you go. Got it. Yep.
And one more. Is that correct?
Yeah, we have one more, which is the binoculars. What? All right, here we go. 833-4868. Oh, Rob, you won the binoculars.
He doesn't believe it. He says so. What do you get?
He won the 15 by 70 binoculars.
All right. Thank you. Thank you.
You're welcome. Yep, that's it. All right, thank you everyone for tonight and welcoming us and joining us on the general meeting tonight. And thank you again to Warren for his fantastic talk. Wow, it was really cool.
Do we know when we're going to be inside the... I'm assuming... Let's just let everybody know.
Yeah.
Because everybody has to be... Assuming that Dave Nakamoto is well enough in July, we're going to get him to run the planetarium for us. And that is a meeting which cannot be Zoomed. You have to actually be here in person in order to sit in the planetarium and look at it with the binoculars and see stuff going around, right? And so I don't know yet for sure whether Dave's going to be well enough. If he is, that's what we'll do. If he isn't, we'll push him off until August. So are we all done? We're all done. Thank you. Good night.